Two more examples to go. Let's get into example number 3 here. This example is pretty much repeated for you on page 748 and 749. They take you through ammonia, so you should take a look at that one. But what we want to do here is calculate the pH of an ammonia solution, very much like Windex or something like that. So, for calculating pH then, obviously we're going to be missing some information. Don't forget, Ka and associated Kb values are available for us on the data table. So if we're going to want to solve this one, we might need to go to the data table for that one. All right, so here we take a look at our entities. We're trying to figure out the proton transfer here. Water is both potentially an acid and a base. Yes, that is water. And ammonia is only on the base side of the table. You'll find it down near the bottom right. So we have two potential bases, one potential acid here. Water is by definition then the strongest acid in the system, and ammonia becomes our strongest base as it's slightly as it is superior to water when we take a look at the base side of things. This means that the proton transfers between water and ammonia. And so we get this as our equation. All right, ammonia exchanges proton, gains it from water to form the ammonium ion and hydroxide ion. So you'll see that we'll be able to calculate pOH directly once we can figure out the amount of hydroxide, and then we'll convert that to pH for our answer. To complete the table then, we take a look at what we've got. And so we have a 0.10 ammonia solution. Water doesn't play. Zeros for ammonia, the conjugate acid, and hydroxide, which will be used to solve our problem. In this one, though, because we lack pH and pOH, it's something that we're calculating, we don't know the amount of change that we have. All right, but if ammonia is going to make an amount of hydroxide, then it does have to lose and decrease concentration. Therefore, it would decrease by a factor of x. Our final concentration here would be 0.1 minus x. We use stoichiometry to predict that these are increases by x. And so, again, we have that blasted unknown existing in our ice tables. But in chapter 16, we are going to assume that the change is insignificant. Most of these things would have very, very small ionization constants and shouldn't change in their concentration all that much. So, we take a look at this one, and we're looking at ammonia as a base, and so my equilibrium law expression here would be Kb. I need to calculate Kb's because they're not given to us, unless the question was being really nice and I stated it in the question. These are things that we'll have to calculate from our data table here. So I'm looking for ammonia, which I find down here as a base, and the conjugate acid for ammonia is the ammonium ion we saw in this expression. Ammonium relates to a Ka of 5.6 to the negative 10. Ammonia, missing its Kb value, we just need to figure out what it is. So, we can go do that. There's Kw divided by Ka to give us the equivalent Kb. This would be for the conjugate acid in the system of ammonium, and we get 1.75 times 10 to the negative 5. I now have a number that I can put into my equilibrium law expression to hopefully start solving for the hydroxide ion concentration. So here I go. There's my Kb. There's ammonium and hydroxide. And then there is the equilibrium concentration of ammonia. I'm assuming that there is an insignificant change in its concentration. Remember, we can test these things. We're not explicitly asking you guys to do this with at-home learning. All right, but we do look for that rule of 1,000. All right, just like if we were to test the concentration of an acid and divide by Ka, we can test the concentration of a base and divide by its Kb. And if the number is greater than 1,000, then you're looking at an insignificant change. This one works out to 5,600, so I can use the ignore x strategy and solve for x as 0.001336. That is now the difference here, the increases here, and the resulting concentrations. So, by definition, I now have the concentration of hydroxide. I can calculate pOH from my hydroxide ion concentration. That is the negative log of OH minus. That's the negative log of X in this case, or the negative log of 0.00133. Run that through your calculator and you get a pOH of 2.87, but we like to talk about things as pH rather than the less popular pOH, and so we can just use that subtraction formula. pH is just equal to 14 minus the pOH, or 14 minus 2.87 to give us 11.13. Okay, so very, very similar. The only things that are changing in these problems here between what we were doing before is there's usually a calculation of a Kb to use in the expression. If an equation is producing hydroxide, then we're talking about a basic system. It makes most sense to talk about the equilibrium law in this case as a Kb rather than a Ka, because hydronium doesn't exist in the expression. At least we don't see it. There's a reduced amount there to give us a very high pH number, but we're looking at it from the OH minus point of view. All right, hopefully that one makes sense. I'm just going to show you number 4 really, really quickly. It's the same question as number 3, but we won't see anything like it on your test because we're not going to deal with anything that is going to fail that rule of 1,000. You can see in the numbers here that your weak base is 1 times 10 to the negative 2 moles per liter, and the Kb is also on the order of magnitude of times 10 to the negative 2. Obviously, these guys aren't going to have a rule of 1,000 safety check. You're going to get something that is a very small number, which means the amount of ionization that you get is going to be significant, and we will drastically change the number. In order to calculate that correctly, you would have to use the quadratic formula to get an accurate answer. So, but just to show it to you guys here really quickly. All right, we're not really looking at it at home learning like this, but here you have your weak base, water, your conjugate acid, and hydroxide. We have a fairly small concentration for the base. Minus X would be my equilibrium. Plus X would be my equilibriums for the products. I do a quick test to see if it passes the rule of 1,000, and I find out that it is definitely not greater than 1,000. So the answer could not be accurate if I was to ignore X. All right, there you go. That's the remaining example that we had. Your last practice assignment, page 746, numbers 10 to 13, number 750, questions 1 to 8, and 10. I would try a few of those, make sure that it makes sense, and yeah, it should be good. Remember the Chapter 16 review at the back of the textbook and all of the additional diploma prep stuff that we see in D2L under this Chapter 15, 16, the equilibrium stuff. So your Chapter 16 test is coming up this week, and it will only be Chapters 16.1 to 16.3. We are ignoring and omitting 16.4. We do not need to get into pH curves, since we did it last year. And we can ignore the polyprotic species and things like that. So if you're looking at chemistry for next year, maybe take a brief read through it, but nothing 16.4 will make it to your test. Good luck with your studies, guys. I will see you in our next video tutorial, which is happening on the day of your quiz. And yeah, any questions you have before attempting the quiz, certainly check into that meeting. Good luck, guys.